So the next video from chapter 15 is going to be on fluid flow and Bernoulli's equation, and this covers some of the things in chapters 15-6, 15-7, and 15-8. Okay, so first off, fluid dynamics is the study of fluids in motion. So up to now, when we looked at pressure versus depth in a fluid, and Pascal's principle and Archimedes' principle, we were interested in fluid statics, so fluids at rest. Here we're looking at fluids in motion. And we're going to concentrate on the simplest case. And this is called streamline or laminar flow. So that's smoothly flowing instead of think, sort of a slow moving river, instead of turbulent flow, which is like rapids. So zero viscosity. So viscosity, remember, is the resistance to fluid flow. So it's sort of like the frictionless case when we did linear kinematics. And we're also going to be looking at incompressible fluids. So remember, this is ideal fluids. So our fluids are incompressible, so the density of the fluid is constant and not changing. So the first useful thing is something called the continuity equation. And the continuity equation, well, first off, we need to define something called the mass flow rate. And the mass flow rate is just the amount of mass per unit time that passes some region. So imagine you have a pipe, and let's say the pipe gets smaller or the pipe gets bigger, whatever. But you can measure, so say take a look at one particular point and you just count how much mass passes in a particular unit of time. So the continuity equation states that the mass flow rate has to be the same. So or another way to think about it, the mass flowing in has to equal the mass flowing out. So imagine you have some pipe and perhaps the pipe changes in diameter. But even with the change in diameter, right, so if you're pushing some amount of mass per time in, then that same amount per mass has to come out. And that's just the continuity equation, which says that the mass can't be created or destroyed. So the mass that goes in has to come out. So if we do a little bit of math, if we have, the amount of mass flowing through one point in this time interval equals the amount of mass flowing through the other point in the same time interval. So we can, if we do some math, we can say that the density at point 1 is equal to the area, the cross-sectional area of the pipe at point 1 times the fluid speed at point 1 times the density area volume at point 2. Now, we can now define the volume flow rate. So the volume flow rate is the amount of volume per time, or you could think of it as the cross-sectional area of your pipe times some length over time, and length over time is a speed. So this is A times V. And remember, we're interested in ideal fluids where the density doesn't change. So if you look at this equation up here, the density isn't changing, so the rows are the same, we can cancel them out, and you wind up that the volume flow rate is a constant. So A1 V1 equals A2 times V2. Okay, and finally, Bernoulli's equation. So Bernoulli's equation describes the streamlined flow of an ideal fluid. And here it is. And if you look at everything at one point in the equation, that has to equal this quantity at the second point in our fluid flow. Sorry, this should be a plus sign instead of an equal sign here. So the pressure at point 1 plus 1/2 rho V1 squared plus rho Gy1 squared equals the same thing at some other point in your pipe or your fluid flow. And this is really just conservation of energy. So the pressure has to do with the work. The 1/2 rho V squared, well, that should look suspiciously similar to kinetic energy. And the rho Gy should look suspiciously similar to gravitational potential energy. And basically one of the important points to get out of this is that the pressure of a moving fluid is inversely proportional to the velocity of the fluid. So if everything else stays constant, if the velocity of the fluid increases, the pressure has to decrease.